Hi everyone, my name is Hugo Blanc. I'm a third year PhD student at Paris School in France, and today I'm glad to present to you a new research paper, Hermite Radial basis functions for surface reconstruction via differentiable rendering. In this paper, we ask ourselves the questions, how can we reconstruct a surface using local basis functions and differentiable rendering? The main idea was to leverage the different works that have been done in the domain of novel synthesis by volumetric rendering. For instance, works such as neural radiance fields, Raygaud, or Gaussian splatting. In those works, they represent the scenes with the density and the radiance fields, and they obtain really high quality novel synthesis results. However, one weakness for our task is that it doesn't include any explicit surface representations. So the first thing to address was to introduce the notion of surface into this representation. Different work try to introduce the notion of surface into the volumetric rendering equations, for instance, nus and object as volume approaches. In those papers, they introduced an implicit functions such that the surfaces of the scenes are represented by the zero-level set of these implicit functions. Then they defined a new density wide such that the rendering weight in the volumetric rendering equation are concentrated near surfaces of the scene. Before presenting our approach, it is useful to look at a closely weighted problem that has been extensively studied in geometry processing: surface reconstruction from point clouds. In this setting, the input is a point cloud and the goal is to reconstruct a continuous surface from these discrete samples. A very common strategy, as discussed previously, is to represent the surface implicitly by defining a scalar function f of x, and then extracting the surface as the zero-level set, that is, all points such that f of x equals 0. Many classical methods model this function using radial basis functions, or RBF. The function is fitted not only to the surface samples themselves, but also to additional offset constraints located slightly inside and outside the surface. This helps enforce the sign structures of the implicit function and improve the stability of the reconstructions. The figure on the right illustrates this idea. Starting from point samples shown on the left, the implicit function is optimized and the reconstructed surface is then extracted from its zero-level set. This line of work is particularly relevant to us because it shows how geometric structure can be recovered from sparse samples for implicit representations. Among implicit reconstruction methods, an important family is based on Hermite radial basis functions, or HRBF. The main idea is to define the implicit function f as a weighted combination of radial basis functions on one part and their spatial derivatives on the other part, together with a low-degree polynomial term. What makes HRBF particularly interesting is that they naturally incorporate both positional and normal information. Instead of only enforcing that the surface passes for the sample points, the method also constrains the gradient of the implicit function. More precisely, for each sample point mu, we enforce two conditions. The point must lie on the surface, meaning f of mu equals 0, and the gradient of the function must match the observed normal direction so that the gradient of f is equal to the normal. These Hermite constraints provide much stronger geometric information and typically lead to smoother and more accurate reconstructions. The examples at the bottom illustrate this process. Starting from a sparse set of oriented point samples, shown with normal inwards, the HRBF formulation reconstructs a continuous implicit surface that preserves the underlying geometry. Building on these reconstruction methods, our approach combines both HRBF-based implicit surfaces with differentiable rendering. The key idea is to start from an oriented point cloud and use it to initialize an implicit surface representation. This gives us a geometrically meaningful prior from the beginning of the optimization. More specifically, the input to our method consists of two elements. First, a set of multi-view images is used for rendering supervision, and second, an oriented point cloud providing positions and normals, which can come from sources such as LiDAR, multi-view stereo, or 3D scanners. Using these oriented samples, we construct an initial implicit surface with the HRBF formulation presented previously. However, the initialization is only the starting point. We then refine the surface for differentiable rendering. At each iteration, the current geometry is rendered into the input camera views, compared with the observed images and optimized using image-based losses. This optimization progressively improves the geometry and recovers finer surface details that may not be present in the initial point cloud. As shown on the right, the final result is a refined implicit surface with significantly higher geometricality, while still preserving the strong structural prior provided by the RBF initialization. Let me now describe our representation. We represent surfaces using an HRBF formulation, where the implicit function f of x is defined as a combination of radial basis functions, their gradient terms, and the constant offset term p0. In our formulation, the basis functions are localized kernels, such as Gaussians or one-line functions. This allows to limit the influence of each point to a local neighborhood. We also use a positive constant term p0 to avoid boundary artifacts, and more details about this choice are provided in the paper. To make this representation compatible with differentiable rendering, we adopt the object as volumes representation and define a volumetric density from the implicit field. To use the volumetric rendering equation, we also define a radiance field representation. The emitted radiance is modeled as a weighted combination of local radiance functions. The weights are computed from localized kernel centers at position mu, which provides a smooth spatial interpolation between local appearance components. The radiance itself is view-dependent, and in our implementation, we use a combination of spherical harmonics and spherical Gaussians. This representation is fully compatible with volumetric rendering while remaining local and compact. Once the representation is defined, all scene parameters are optimized gently through gradient descent. This includes the HRBF coefficients, the kernel positions and scales, as well as the radiance parameters. Our training objectives combines two terms, a rendering loss and a regularization loss. The rendering loss measures the discrepancy between rendered images and ground truth views. In practice, we use a combination of SSIM and L1 losses. The regularization term is applied to the HRBF coefficients and helps stabilize the optimization by penalizing large parameters values. Overall, these objectives allow the geometry and appearance to be refined directly from image supervision while preserving a coherent implicit surface representation. Finally, let me present some quantitative results on the DTU dataset. These tables compare the method with several recent reconstruction approaches using chamfer distance as the evaluation metric together with training time. Overall, our methods achieves competitive reconstruction quality across the different scenes while maintaining relatively low training times. In particular, we obtain one of the best average chamfer distances among compared methods, while remaining significantly more efficient than many neural implicit approaches. This suggests that combining HRBF-based geometric pairs with differentiable rendering provides a good balance between reconstruction accuracy and computational efficiency. Here we show quantitative reconstruction results on the DTU and tungsten temples datasets. On the left, we compare our method with recent approaches on several DTU scenes. The highlighted regions show that our reconstruction preserves finer geometric details and produces cleaner surfaces in challenging areas. On the right, we present the results on the tungsten temples dataset. The reconstructed surface is shown on the left, while the corresponding rendered image is compared with the ground truth views on the right. Overall, these results illustrate that our method can recover coherent geometry and high quality rendering across different types of scenes. Finally, we conclude with additional qualitative results on the blended MVS datasets. The following video shows the reconstructed geometry from different viewpoints, illustrating the consistency of the surface and the level of geometric details recovered by a method. Thank you for watching this video, and please refer to the papers for more details about the formulation, the implementation, and additional experiments.